Have you ever looked at a car engine or a complex robotic arm and just wondered, how does it do that? How does it achieve such precise, powerful movements? Well, it's not magic. It's actually a language, a kind of secret language of motion written with the principles of kinematics and dynamics. And today, we're going to learn how to speak it.
All right, so here's our game plan. We're going to start with the absolute basics, the alphabet of machines. Then, we'll see how we can use that to predict how they'll behave. After that, we'll dig into the forces at work, and finally, we'll look at a couple of incredible components that literally choreograph motion and guard a machine's speed. Let's get into it.
Okay, first things first. Just like any language, we gotta learn the ABCs. These are the fundamental building blocks you'll find in pretty much every machine out there. Once you see them, trust me, you'll start recognizing them everywhere.
So, it all starts with this, the kinematic link. Every single machine, no matter how complicated it looks, is built from these individual rigid parts. You can think of them as the bones of the machine's skeleton. Their whole job is to carry and transmit forces from one spot to another.
Now, a link by itself is it's just a part. The real magic happens when you connect them, and that connection is called a kinematic pair. This isn't just any connection. It's like an elbow or a knee in your body. It's a joint that's specifically designed to allow only certain kinds of movement.
And these joints, or pairs, basically come in two main flavors. You've got your lower pairs, which have a lot of surface contact. Think of a pin rotating inside a hole. They're super stable and built to last. Then you have higher pairs, where the contact is just a tiny point or a line, kind of like a cam pushing on a follower. These allow for way more complex and specialized motions.
So you take these links, you connect them with pairs, and when you arrange them to form a closed loop, bam! You've got what's called a kinematic chain. This is it. This is the complete skeleton of your mechanism, all ready to be put into motion.
So we've built this skeleton, but how does it move? Or can it even move? Well, we don't have to guess. There's this brilliant formula, Kutzbach's criterion, that lets us calculate exactly how many ways it can move, its degrees of freedom, just by counting the links and the joints. It's an insanely powerful tool for engineers.
All right, we've got the vocabulary down. Now for the really fun part, using some surprisingly simple rules to predict really complex movements. This is where we start forming sentences with our new language.
Check this out. Grashoff's law. It sounds a little intimidating, but it's basically a cheat code for one of the most common setups, the 4-bar linkage. Just by knowing the lengths of the bars, this simple little formula tells you if any of them can spin all the way around in a full circle. It's a game changer for design.
And this leads to this really cool idea called inversions. Get this, you take the exact same 4 bars, but just change which one you bolt down to the table, and you get completely different machines. If you fix the one next to the shortest link, you get a crank rocker, perfect for a windshield wiper. Fix the one opposite the shortest, and suddenly nothing can spin all the way around. Same parts, totally different motion.
And this isn't just some abstract concept. It applies to the slider crank mechanism. You know, the thing at the very heart of your car's engine. Fix the frame, you get an engine. Fix the crank, you get a quick return mechanism. Fix the slider, and you get a simple hand pump. One chain, so many different machines. It's just elegant.
Okay, so we can predict how things are going to move. Now let's get into the nitty-gritty of the forces and speeds involved. And we're going to talk about one force in particular that's, well, it's a little weird, but it's absolutely crucial to understand.
So, I want you to picture this for a second. Imagine you're on a big spinning merry-go-round. Now, what happens if you try to walk in a perfectly straight line from the center out to the edge? You're moving straight, but your whole path is rotating underneath you. This creates
And that effect is Coriolis acceleration. It feels like this phantom force that comes out of nowhere, pushing you sideways. But it's totally real. It exists purely because your frame of reference, the merry-go-round itself, is spinning.
So the key takeaway here is that you only get this Coriolis effect when two things happen at the exact same time. One, a link has to be rotating. And two, a slider has to be sliding along that rotating link. If you don't have both, the effect just disappears. Simple as that. All right, let's shift gears and talk about one of the most clever ways to control motion with incredible precision. Let's talk about cams and followers. You should think of them as the choreographers of the mechanical world. And just like any good choreographer, they come in all sorts of shapes and styles. You've got disc-shaped cams, cylindrical cams,
Then you have followers with knife edges or rollers or flat faces. All this variety lets engineers create these very specific, perfectly timed dances of motion to do things like open engine valves or guide parts on an assembly line.
Of course, you can't have the follower just jerking around. It would shake the machine to pieces. So, engineers design its motion to follow a very specific, smooth, mathematical curve. A really popular one is simple harmonic motion. Yeah, the same gentle motion as a pendulum swinging back and forth. This provides smooth transitions, which means less vibration, less noise, and less wear and tear.
Okay, last big topic for today. Let's say you've got this powerful engine. How do you keep it from running too fast or slowing down too much when the workload changes? You need a guardian of speed.
And that guardian is the governor. This thing is basically the original all-mechanical cruise control. It's a brilliant device that senses the engine's speed and, all by itself, automatically adjusts the fuel to keep things running steady. There are no electronics here. This is just pure, beautiful physics at work.
These were absolutely essential back in the day. The huge steam engines that powered the Industrial Revolution, they relied on these clever designs, like the Watt and Porter governors. They literally used spinning balls and the laws of physics to sense speed and control the most powerful machines of their era.
So let's bring it all home. This secret language we've been learning, this world of links and pairs, forces and cams, it isn't just some abstract theory. It is the foundational toolkit. It's what allows us to turn a simple pile of parts into the complex, predictable, and controllable systems that make our world work. And that leaves us with one final big question to think about. As we race forward into a world of advanced robotics and AI, how will these timeless, 100-year-old mechanical principles combine with intelligent software to create the next generation of machines? The language might be old, but the stories it's about to tell are brand new.